Okay, so last time we were talking about the operator algebra for a general angular momentum. And so we had worked out the following things. There's an operator j squared, which when we act on k, j, and m as a state, gives us back h bar squared, j times j plus 1 times kjm. By the way, a common mistake is to think this is the operator j squared, and therefore this should be little j squared, but that's not what it is. So don't be that person who writes little j squared there. Okay, and also j sub z, acting on one of these states, gives h bar times m, that's the last label for the state. Okay, and last time we had worked out some facts about these objects. So I think I called them facts 1 through 7. And they imply, after we played around with them and did a little bit of algebra, that j has to be a non-negative integer divided by 2. And then once you've selected j, then m has to be one of the following values: minus j plus 1, up to j minus 1, and then finally j. And so if you just count those for general j, that's going to make 2j plus 1 values. For each j. Okay, and then we had these other operators, j plus and j minus, which raise and lower the value of m without changing j. And in fact, last time we worked out more specifically what they do, in fact, in terms of what the numerical factors are. But since I'm going to be writing those down later anyway, I'll skip them at this point. Okay, and then of these 7 facts, there's one that we're going to reuse again today. So I'm going to rewrite this one. It turns out to be fact 3 we're going to use in just a little bit. Fact 3, we proved that if you have one of these states, and it's not a null state, in other words, it actually exists, and you act on it with j minus, and that's a null state, that implies, or that happens if and only if m is equal to minus j, which is another way of saying that we're acting with this j minus. It's trying to lower m, but if m is already as low as it can possibly be, then you get the null state. And conversely, if you act with j minus, if you lower m, and you find out that you got the null state, then it had to be true that this m was already minus j. Okay, and then this part of it comes in by saying, if it was actually the null state to begin with, then maybe you were somewhere up here or somewhere down there. Those are states that don't actually exist. Okay, so that's fact 3, which we'll use very soon. And so what our next task is to do is to consider the subspace of states, or subspaces of states. Okay, that's a Hilbert space that's part of the bigger Hilbert space that obeys some properties. And I'm going to call these subspaces S, J, M. And they're distinguished by having fixed J and M. Okay, so we just imagine of all the states in the Hilbert space, we select the ones that have some fixed value of J and M and consider that subspace. Okay, so there's an orthonormal basis for these, which I can label as KJM. This is an orthonormal basis. The only way it's different from the basis that orthonormal basis, I guess I usually call that just orthobasis. The only way it's different from these up here that I wrote down, it's not actually different. It's just that now I'm restricting to some fixed J and M for those states. Okay, and now there's the label K. Remember, K is a degeneracy label. So K is running, let's say, from 1 up to some number G, which is the degeneracy, but that degeneracy depends on what J and M are. So I'm going to put a J and an M on it. This is the degeneracy of the subspace. In other words, just the number of different distinct orthobasis states within it. Okay, and then if it's an orthobasis, that means if I take the inner product, K prime JM with KJM, that's equal to the Kronecker delta of K prime and K. Okay, now what are we going to do with this these subspaces of states? Within them, we're going to consider other states that we're going to define to be J plus acting on the orthobasis states. So we take a KJM, we act on it with J plus, and we do this for various different Ks. Okay, of which there are G sub JM different ones available. And we're going to ask, what are the inner products of these states? So the reason we're asking what are the inner products is we're aiming towards understanding what the orthobasis is for the whole state space. Okay, so to consider these inner products, we'll just compute them. So if we have K prime JM, J minus, remember J minus is the Hermitian conjugate of J plus. So when I take the inner product, I'm using the adjoint of one of these states. So the J plus turns into a J minus. And then I've got J plus KJM. Okay, and this combination J minus J plus we had worked out last time. So we can now state that this is H bar squared times the quantity J times J plus 1 minus M times M plus 1. And then there's the Kronecker delta, delta KK prime. Okay, so it looks like these things are almost orthonormal. In fact, they're orthogonal from the delta KK prime factor, but then there's this funny factor in front. And so to make them be orthonormal, we can just make the following definition. We're going to define K, J, M plus 1 equals J plus KJM. And then we're going to divide by the square root of the previous numerical factor, which is H bar over J times J plus 1 minus M times M plus 1. Okay, so first of all, we know that when we act with the J plus, it's raising M by 1 unit. So that's why this is an M plus 1. And this factor is making it normalized to 1. And we already found that they were already orthogonal. Okay, so what does that mean? Oops. That means that these form an orthonormal set of states. I'm being careful for the moment not to call them a basis because we're not sure that they're a basis yet. But we will prove, in fact, they are. So, but their properties are that their j squared eigenvalue is h bar squared j times j plus 1. And their j sub z eigenvalue is h bar times m plus 1. And so what does that mean? That means they belong to a different subspace. They are in the subspace Sjm plus 1 instead of Sjm. Okay, so they're an orthonormal set of states. And now we're going to ask the question, are they in fact a basis? Are they a basis for this subspace? All right. So the main thing we have to worry about is that since we already know they're orthonormal, we have to worry about whether they actually cover the whole subspace. And so let's suppose they didn't. Let's suppose there was some other state that's not covered. Okay, so suppose there were a state, let's call it k tilde j m plus 1. That's orthogonal to all of the ones we just constructed. So to all of the k, j, m plus 1 that we just defined. Okay, then what does that mean? That means if I write the inner product, k tilde, j, m plus 1, and I'm going to rewrite kjm plus 1 as j plus, acting on kjm. If those were orthogonal, then this would have to equal 0 for all k. Okay, so we're supposing that this state here exists and that it's different, it's orthogonal to all of the ones that we constructed by definition.
Then should that be an m plus 1 on in the ket?
This one? Oops.
Yeah.
No. So when I wrote kjm plus 1, that's this whole thing here.
Okay, thank you.
Yeah. Okay, so I'm rewriting that here, but I'm writing it in terms of j plus, and the reason for doing that is because now I'm going to consider this part of it. Okay, and that part of it is a bra, which corresponds to the following ket, j minus k tilde j m plus 1. So I just take the Hermitian conjugate to form a ket from it. Okay, and so this is something that obeys the following properties. First of all, it's non-null. And the reason we know it's non-null is from fact 3, which I reminded you of earlier. And that's because m plus 1 is not equal to minus j. Right? And the reason we know that is because if m plus 1 was equal to minus j, then m would equal minus j minus 1, and there's no such state in the Hilbert space. So it's non-null. It has j sub z eigenvalue, h bar m. and it has j squared eigenvalue, h bar squared j times j plus 1. Okay, and it's also orthogonal to all the kjm's. Okay, and that's a problem because we assumed at the very beginning, we assumed that they formed a basis. Okay, and so this gives a contradiction because this says, all of this stuff says that they're in SJM. So this is an element of SJM, that subspace. Okay, but it's orthogonal to all the basis elements of that subspace, and that's the contradiction. So we're bootstrapping the fact that we assumed we had a basis for SJM. We tried to construct this thing that would be a state in SJM plus 1. That was not one of the ones that we got from the ones in SJM, and we found it wouldn't work. Okay, so all of that tells us that, in fact, the set of states k, j, m plus 1 that we constructed, which again are defined like this, we take j plus and we act on k, j, m. And then we have a normalizing factor. We had to divide by this to make them be orthonormal. Okay, this is a basis for the other subspace, the next subspace. Okay, so notice that these have the same k labels for the different subspaces. Okay, so we have the same k labels for the states k, j, m plus 1 as for k, j, m. So for every state in the subspace with m, there's a corresponding state, exactly 1, in the subspace m plus 1. And in particular, that means the degeneracies are the same. So when I wrote down the degeneracy, let me write the word degeneracy here. The degeneracy G sub jm, it turns out, is actually equal to the degeneracy of jm plus 1. And so it turns out it was a waste of time to distinguish what the m value was. This can depend on j, but it can't depend on m. That's what we showed. And basically, the idea behind showing this is because we can use the j plus and j minus to move up and down in m without changing anything. And so in particular, that won't change the degeneracy. Okay, so this doesn't depend on m. But it can depend on j, because we don't have a way of changing j like we changed m with the j plus and j minus objects. Okay, and then anything we can do with j plus, we can do with j minus. So similarly, if minus j plus 1 is less than or equal to m, is less than or equal to j, then we can construct k, j, m minus 1 to be the j minus operator acting on the state k, j, m, divided by a normalization factor, h bar square root of j, j plus 1, minus m, m minus 1, it turns out. Okay, and those are a basis for S, J, M minus 1, that subspace. Okay, and then we can do this recursively for each subspace we can construct one with higher m or lower m, just by acting with j plus or j minus, and then including these funny normalization factors. Okay, and so by doing that, we get an orthobasis for the whole state space. So orthobasis for the whole state space which means all j's and m's can be constructed if we just have one of them with one value of k and j. So if we have one representative for each k and j. Okay. So that's pretty remarkable. If we just choose some value of k, that's the redundancy label for the angular momentum states. And for each j, if we know one member of the state space, then we can act with j plus j minus and get all the others. So for example, let's say you're given a state kjj. Okay, so that means m equals j. Then you get all the others that have the same k, the same j, but some other m by repeatedly acting with j minus. Okay, but if you care about normalization, then you also have to worry about the prefactor in front. Okay, or let's say you're given a state k, j minus j, so m is minus j. Then you get all the others by repeatedly acting with j plus. And you could have something in the middle. You could have some state in the middle, and then you act up with j plus until it vanishes. You act down with j minus until it vanishes, and you get all the states this way. Okay, so that's saying there's a complete orthobasis that we can write as states kjm with the following properties, that if I take the inner product of k prime, j prime, m prime with kjm, okay, that's delta k, k prime, delta j, j prime, delta m, m prime. I think I wrote this down last time, but now what we've shown is how to actually construct it. Okay, and if I take a sum over j, and then for each j, I sum from m equals minus j up to j. So I'm summing over all possible states. And I sum k from 1 up to g sub j. We decided the degeneracy can depend on j, but it doesn't depend on m. Okay, if I do the outer product, that's the identity operator. Okay, so this is completeness. Okay, that's the complete part of it. And this is the orthonormality part of it. Which was there. So this is a little bit abstract. In a real problem, you need to know what j's actually contribute and what k's are and how they contribute. So unfortunately, I can't answer that question without committing to a specific problem. So to know what j to sum over, because in some problems, you won't sum over all j. I just wrote it sort of here abstractly, sum over j, but sometimes you'll only be summing over, let's say, j equals 1/2. that will be the only contribution, or maybe j equals 0 and j equals 1 will be the only contributions. So you don't know, just in general. And you don't know what k's are and what they are to sum over. And you certainly don't know what the degeneracies are without committing to a specific problem. Okay, and so to know those, you need to know the specific physical system, and then you probably have to solve some eigenvalue problem in order to figure this out. So need to know a specific physical system. Okay, but typically, k is going to be the eigenvalues of some observables. I'm actually saying plural here because it could be more than one. K could stand for more than one thing. But there's some observables that might be called A, B, etc., that form a complete set of commuting observables with the angular momentum ones. So together with j squared and j sub z, you have a complete set of commuting observables. In most problems that we can all actually solve, it's going to turn out k corresponds to the energy. And those correspond to systems that are invariant under rotations, like the 3D harmonic oscillator. So if system is invariant under rotations, one of them, and often the only one, is going to be the Hamiltonian. So when I say one, it's often the only one, is the Hamiltonian. And so that's saying if you know the energy and the total angular momentum and the z component of the angular momentum, then you know everything there is to know about the state. Okay, so examples of this that we're actually going to do are going to be a particle in a sphere, particle confined to a sphere. That's the analog of the one-dimensional particle in a box, but more realistic because usually physical systems that we're interested in real life aren't in one dimension. Okay, we're going to return to the 3D isotropic harmonic oscillator. We're going to do the hydrogen atom. And we're going to do the free particle, which is a little bit non-trivial in this basis. It's much easier in rectangular coordinates, but it's a fun thing to do, and we'll actually it'll be useful later. Okay, so in all of these cases, the complete set of commuting observables is going to be the Hamiltonian, j squared, and j sub z. But of course, the Hamiltonian is what's going to be different for each of these three cases, which means the k label will be different for each of these cases. Okay, questions so far? Okay, so up here we just said that, okay, we can construct an orthobasis. There's a standard orthobasis that's a little bit more specific. I'll put standard in quotes because, of course, you can choose whatever orthobasis you want. But the standard one satisfying the above equations has the following properties. Okay, so again, J sub Z acting on an orthobasis element is H bar M. That's saying it's an eigenstate of J sub Z. Okay, and then there's J plus. And this is equal to H bar square root of J times J plus 1 minus M times M plus 1. And it gives you back the state K, J, M plus 1. So what I want to emphasize here is that when we write this down, we're actually making a choice of phase. Because all we really proved before is that these things were proportional to each other. Okay, and so you could put, if you're just solving an eigenvalue problem, you can always just put any phase you want right there, and it's still going to satisfy the eigenvalue problem. Okay, but we're choosing the phase to be +1 because why would we choose anything else? Okay, and note also that it's built into this equation that this equals 0 if M equals J, which is good because that was one of our facts that we proved last time, is that that had to happen. Okay, and similarly for J minus, this is J times J plus 1 minus M times M minus 1, and it gives you back the state with M1 lower. And that also involves a choice of phase. And there's a remarkable fact, which is very fortunate, that this choice of phase that I've made right here and this choice of phase that I've made right there are consistent with each other. That didn't have to be true, but it's true that if you choose both of them to be +1 and not some other phase like -1 or e to the 17I pi over 19, you get a consistent choice of phase. Okay, and one way to do that is to act with J plus and then act with J minus and see if you get back the right state. Note this is equal to 0 if M equals minus J, which was another one of our facts that we wrote down last time. Okay, and then again, J squared acting on KJM is H bar squared J times J plus 1 KJM. And again, remind you not to be one of those people who makes the mistake of writing J squared there, which is very tempting, but not true. Okay, so what we've proved up till now is that the matrix representations for these things don't depend on K because, well, one way of seeing it is if we just stare at this whole set of equations that defines how the operators act, you notice there's actually no K anywhere in any of these coefficients. And because there's no K there, when we construct the matrices for these, there won't be any Ks in the matrix either. And therefore, the matrices that represent these operators will not depend on K. Okay, so the matrix representations for J squared and J, the vector, which includes within it Jx, Jy, Jz, J plus, J minus. These all don't depend on K. In other words, you can think of that as saying they don't depend on the energy, for example, in some three-dimensional system. So what that means is we can work them out once, and then it's good for every physical problem that we do, including all the possibilities mentioned earlier. So can work them out once. And then once we've done that, they're good for all physical systems that we choose to apply them to. Okay, and so we're just going to go ahead and do that, starting with the simplest one and seeing how far we get today. So the simplest one, of course, is going to be the J equals 0 subspace. So if we go back up here and look at what these are, if J equals 0, that implies that M also must be 0. So that's 0. This is 0. That's 0. 0, 0. Everything's 0. Okay, and so that means J sub Z and J plus and J minus, and I should write equals here, I guess. Okay, so J sub Z, J plus, J minus, Jx, Jy are all just 0. J squared is equal to 0. And so we can think of these as a 1-by-1 matrix of zeros. And so there's only one state space element for each k. Okay, and so I can write here k, j equals 0, m equals 0. And any angular momentum operator acting on that just gives back 0. So that was too easy. Let's do the next one. And the next smallest one is the j equals 1/2 case. Okay, and so first let's write down the orthobasis. Okay, and I'm going to skip the k label because it just goes along for the ride. And so first of all, there's a state j equals 1/2, and m can be 1/2. And we can write that as the state up arrow. And this corresponds in matrix notation to the vector 1, 0. And then there's a state that also has j equals 1/2, but m equals minus 1/2, which is sometimes known as the state down arrow. Some books will call those the states plus and minus, or even 1 and 0. I don't like 1 and 0 because if anything, I would call them 1/2 and minus 1/2, but some books do it that way. But anyway, the matrix representation for this is 0, 1. Okay, and so because those are two-dimensional vectors, which comes because there are two of them, that means the matrix representations for all of our angular momentum operators must be 2 by 2. Okay, and so in particular, J sub Z is, I shouldn't write equals, technically, I should write corresponds to. In matrix language, this is h bar over 2, 1, 0, 0, minus 1. And J squared is h bar squared. It's proportional to the identity operator, 1, 0, 0, 1. And then going along with the theme of not being the person who makes the mistake of saying j squared there, this is j times j plus 1, which is 3/4. Okay, so there's a 3/4 there, strangely enough, in the j squared matrix representation. And then we can work out what j plus and j minus do. So for example, j plus acting on the state 1/2, 1/2, which I could equally well write as up arrow, that's equal to 0, because if my m value is as large as it can possibly be, and then I try to raise it more, I can only get the null state. Okay, and if I act instead on the state with minus 1/2, then I have to go back to the formula This was up here. Basically, I'm going to be using this. Okay, and so I just plug in the numbers. This is h bar square root of 1/2 times 3/2 minus 1/2 times 1/2, acting on 1/2 1/2, because I raised my m value. And this inside the square root turns out to be 3/4 plus 1/4, which is 1. And so this is just h bar acting on the state 1/2 1/2. Okay, so now we know how J plus acts on all the states, of which there are only 2 in this example. And so now we can write down the matrix representation for J plus. Summarizing the previous 2 lines, it's equal to h bar acting on 0, 1, or multiplying 0, 1, 0, 0. Okay, so the way that worked is this statement right here is saying that this acting on any vector gives 0. That means this has to be 0 and that has to be 0. And this statement right here is saying if we act on the second vector, we get h bar only if it's the lowered one. Okay, so, and then we get back plus 1 times h bar, that's this element, and we don't get anything with the minus 1/2 state. So that's how that becomes 0. Okay, and then similarly, you can repeat all the steps for J minus, and you find out it is represented by the matrix h bar 0, 0, 1, 0. And now once you've got J plus and J minus, you can construct Jx and Jy. And this is a common theme. It's often easier to work things out in terms of J plus and J minus rather than Jx and Jy, but then you can convert them. So how do we convert them? In particular, Jx by definition is the average of J plus and J minus. Okay, and so the matrix representation for that is h bar over 2, 0, 1, 1, 0. And similarly for Jy, now there's a factor of I that I can never remember if it's plus or minus, but it says here it's 1 over 2i, J plus minus J minus, which means it has the matrix representation h bar over 2, 0 minus I 0. Okay, so now we know the matrix representations of basically everything. We've got Jz, we've got J squared, we've got J plus, we've got J minus, we've got Jx, we've got Jy. Okay, and this set of equations of matrices is called a spin 1/2 system. And again, what we showed is that this works for any spin 1/2 system. It doesn't matter the actual physical case. And so in that situation, we call it S. J is S specifically. And we write S sub Z. I'm just going to write an equal sign here. Many books don't distinguish between the operator and its matrix representation. So temporarily, I will follow that. S sub Z is h bar over 2, 1, 0, 0, minus 1. S sub X is h bar over 2, 0, 1, 1, 0. S sub Y is h bar over 2, 0 minus I 0. And no matter what, this can't be an orbital angular momentum. And it can't even involve the orbital angular momentum without anything else, because we showed that for orbital angular momentum L, then M had to be an integer. So because here we found that M is not an integer. Okay. So obviously, if you're dealing with a spin-a-half system, which is very common, these are an important thing to be able to work with. And so Pauli worked out a bunch of simplified rules for these. These are called the Pauli matrices. The Pauli matrices are you just strip off the h bar over 2 because it's too annoying to deal with. And so this is 0, 1, 1, 0 for sigma x. Sigma y is 0 minus I, 0. Personally, I can never remember which one is I and minus I. I have to look it up every time. And then this one is 1, 0, 0, minus 1. So one thing you can do is you can assemble them into a vector. So it's sigma x in the x direction plus sigma y in the y direction plus sigma z in the z direction. X hat, y hat, and z hat are the unit vectors. Okay, and then having done that, you can say that J is equal to S is equal to h bar over 2 times the sigmas. So really, S here is the operator. And the sigmas are the matrix representation. But we've sort of agreed not to worry too much about the difference. Okay, so there are some nice properties for each of J equals X, Y, and Z. Each sigma J squared is equal to the identity as a 2x2 matrix. And if you take sigma J, sigma K, plus sigma K, sigma J, that's equal to 0 if J is not equal to K. Together, these are saying the anti-commutator of sigma J with sigma K is twice the Kronecker delta of J and K. So that's the anti-commutator, and then the commutator of sigma J with sigma K is equal to 2 times I times a sum over L, which is often suppressed. Oops, that should be JKL. Sigma L. So these are in disguise the angular momentum commutation relations. They are built into the matrices. Okay, and this should have been an L. And L is summed over implicitly. Okay, and then other useful things are the trace of any Pauli matrix is 0. The determinant of any Pauli matrix is equal to -1. Okay, and then you can do things like dot the vector of Pauli matrices into some other vector. So A here is just some ordinary vector. Now it could be an operator as well, but the key thing is it's not a matrix. And it's not an operator on the spin part of the Hilbert space. So it could be acting on some other part of the Hilbert space, like the radial coordinate or something like that. Anyway, you just plug in the sigma matrices, and this is AZ, AX minus AY, AX plus AI, AY, and minus AZ. Okay, and then you have some neat identities like A dot sigma acting on B dot sigma is equal to just A dot B. Notice the Pauli matrices went away there, plus I A cross product B dotted into sigma. Okay, and of that, of those possible relations, the most valuable one usually is the following, that if A and B are the same, and so if I take A dot sigma and I square it, I just get the magnitude of A squared, which is otherwise known as the sum of the X and Y and Z components squared. Okay, so that's telling you you can have an operator that involves spin, but if you square it, you get something that in spin space is proportional to the identity matrix and doesn't involve spin or is independent of spin. Okay, so that's it for today. Sorry I went over a little bit. And let me ask if there are any questions.
I have a question, Professor.
Okay.
Thank you for the lecture. I'm just wondering, are these model, is this based on like real electron spins, how they came up with all of these? Does this have anything to do with the real spin of electrons, or is this all in theory?
No, this absolutely has to do with electron spin. Yeah, this is exactly how you describe the electron spin and every other spin 1/2 particle too.
And are these based on the Stern-Gerlach experiment?
I think the Stern-Gerlach experiment went into this. That was, I think the original Stern-Gerlach experiment was a little bit different in the sense that it involved atoms and so involved more than one possible spin, although I don't remember if it was actually in a spin 1/2 state or some other state. But in principle, yeah, you can describe Stern-Gerlach type experiments with this formalism.
And what are some of the applications of these?
So I mean, they're really just too numerous to mention. I mean, anything involving spin, you basically have to use this if you're going to describe it quantum mechanically.
All right. Thank you. I just have a question from maybe I need to review it again. I did send you an email on this. I was a little bit lost